So we're going to be focusing on how to use EBS with EC2 to scale your big data processing platforms to scale to meet growing demand while improving availability, cost, and performance. I'll be reviewing our new EBS Volumes we launched earlier this year, designed for big data workloads, very shortly, and then we'll have 2 customers come talk to you about how they started leveraging those to improve their platforms for both cost and efficiency. We have Zendesk, who's going to be talking about their ELK stack, and then we have Videology, who's going to come and talk about their Hadoop platform, which they re-architected with EC2 and the new EBS Volumes to ingest, process, and analyze logs. So storage options for big data. You've got a lot of options with Amazon Web Services, from file storage with our simple and scalable elastic file system that went GA earlier this year, which allows you to connect multiple instances to a single file system. We also have block storage options with EC2 Instance Store and EBS, which you can attach to an EC2 instance or to an EMR cluster, as well as our globally accessible and highly scalable object storage with simple storage service. Big data can encompass a lot of different platforms. We certainly understand that. A lot of times S3 will act as kind of a data repository or data lake. And anytime you run any processing or compute on that, we have services you could use like DynamoDB, Redshift, et cetera. But anytime that you're using something like a Hadoop platform or Kafka, where you need to spin up EC2 instances, you have to decide what storage option you're going to choose for that, instance store or block store. So we're going to be focusing primarily today on EBS. There's a lot of benefits to using EBS. There's data persistence, so anytime you stop your server and restart it, that data is still there, which allows you to right-size your instance based off the memory and compute rather than the storage. It opens up a lot more options to what EC2 instances you choose, as well as it's easier to detach and reattach to new instances when growing your clusters out. It also has better security, or easier to manage security, I should say, with our EBS encryption, and it has snapshot capabilities for backup, and also really good volume monitoring with our CloudWatch metrics. So earlier this year, we announced 2 new EBS volumes. Both are magnetic. They're throughput optimized ST1 and SC1. You may have asked yourself at the time, why in the world of high performance and low cost SSD disk would we focus on spinning magnetic media? Well, as it turns out, all this data out there that's being generated that needs to be ingested, stored, processed, and analyzed to help your company make faster, more intelligent decisions, largely can be sequential in nature, which makes a really good fit for magnetic media. SSDs are great for random I/O operations, things like boot volumes, relational databases like SQL, MySQL, Oracle, non-relational databases like Mongo, Cassandra, and Couch. Kind of data where it's broken up into small random access I/O operations. With magnetic media, when you're accessing a block, the disk actuator arm and the head have to move to find the correct track, which is known as your seek time. And the disk has to spin underneath it to find the correct sector, which is known as your rotational latency. So the speed of these operations really depends on how fast that disk can spin. With the advent of SSDs, you no longer have a disk actuator arm, and you no longer have the spinning platter, so the speed to access those blocks improves greatly. So it's not really that big of a concern. But when it comes to sequential data, we don't have that same penalty of seek time and rotational latency, because the block that it accesses is located directly after the previous block, and the head encounters it right afterwards, incurring no wait time. So we took this as a challenge, and we asked ourselves, could we take advantage of low-cost hard drives to come up with a high-throughput storage option that delivers consistent performance? And the answer is yes, and we did. In April, we announced a pair of new low-cost, high-throughput optimized volumes designed to take advantage of the scale of the cloud to deliver high throughput on a consistent basis for use with Amazon EC2 and EMR clusters. Like the existing general purpose volumes, which is SSD based, the new volumes measure performance, or actually I should say the new volumes have a base performance, burst performance, and a burst credit balance. But whereas the SSD volumes measure performance in terms of IOPS, the new volumes measure performance in terms of throughput. So this is really good for a variety of different workloads, but it's really good, and what we're thinking of when we designed it was a lot of big data-oriented workloads like Hadoop, where they are largely sequential in nature and you're pushing large sequential I/O blocks through, Kafka, media streaming, log processing, all kinds of different things, media streaming as well, so all kinds of things that use sequential data. The two different volumes are very similar, but they differ in the way they offer throughput. Otherwise, they're pretty much identical, and the price is different as well. So with the ST1 volumes, you've got a 40 megabytes per second base performance, and it could burst up to 500 megabytes per second. And the capacity is 500 gigabytes to 1 terabyte. So this is great for ideal for large block, high throughput sequential workloads. And then we have SC1, which is identical except that the burst buckets and balance are different. So with SC1, you have 12 megabytes per second. You can burst up to 250 megabytes per second. So whereas ST1 can burst up to 500 megabytes, the new ones can burst up to 250 megabytes. Capacity is the same. We release these, we say they're ideal for logging and backup and cold data, but we actually have a lot of customers that are using them for Hadoop and Kafka and different workloads as well, where your throughput needs might be a little less. The benefit is that they're only 2.5 cents per gig, so they're a lot cheaper. So what these do is they give you the option now. In the past, if you were looking at a high throughput option with EBS, you were probably looking at GP2 or IO1 provision IOPS volumes, and you probably didn't care about the IOPS that came with it. You just wanted the throughput. So now you could right-size your instance for cost efficiency with the new volumes for much cheaper and get a lot more throughput with them, which can help fit these needs. So with that being said, I just want to give an overview of these new volumes and kind of where we came from. I'm going to have Zendesk come to stage and talk about how they re-architected their ELK stack using some of the new EC2 instances and new volumes, and then we'll have Videology come talk to you after that.
Okay, great. We'll just pass the mic. Hi, everyone. I'm David. This is Kyle. And how do we advance here? First, a moment about Zendesk. If you don't know Zendesk, we build customer relationship software. Hopefully, we have a lot of customers in the audience. We have, as you can see, quite a few paid customers, 87,000 accounts all over the world who use our software to satisfy their customer service needs. And here's some logos of some of our great customers that we help. So we're here obviously because quite a bit of our solution runs in AWS, as well as quite a bit of our internal systems used in dev, test, and staging run in AWS. So as David sort of mentioned at the start, what we want to bring to this session is we want to talk about how we utilized the new EBS storage types to improve one of our larger and more expensive internal systems, and that is our logging system based on ELK, which is a very important part of our engineering process, and our production systems enables us to debug and do everything you do with a logging system. I want to talk through some of our design choices as to why we redesigned the system, as to some of the choices we made, explain some of the new benefits, and in the end, it worked out really great for us both in performance and in cost. So with that, I'll hand it over to Kyle.
Hello. So I'm going to talk a little bit about how the technology changes went. And I'll give a little background for people who aren't familiar with ELK. So ELK is made up of three main components. Elasticsearch is the data store meant for ingestion and searching of the data, used for storage. This is where we primarily chose to spend our energy because that was where the most cost was spent due to the storage and the high performance needed because of Elasticsearch. And Logstash is used for ingestion, normalizing, and parsing, and then Kibana is built on top of that as a visualization tool. So when we kicked off this cluster around 3 years ago, the EBS volume choices were quite limited. You really only had SSD choices, and the billing model was such that you were actually charged for the storage allocation as well as the bandwidth on top of it that you were using. So when we factored all that in, we realized it wasn't really cost sensitive to use EBS at the time when you factored all those in. So the initial cluster we built on top of the I2 instances inside Amazon. I2s have very good high I/O throughput. We utilize the local SSD ephemeral storage. Elasticsearch is naturally distributed in nature, so the need for redundancy is built into the cluster. So we didn't necessarily need the redundancy that EBS provides. And this served us well for quite a long time. But as anything does, it began to show some pain points. This is meant to represent how many outages we had inside of our cluster. Pretty much an outage a day. So what we started to see were a lot of operational overhead issues. And that is kind of what we looked like at the time. My slides messed up. All right, so a few of the problems we hit. First was around operational headaches. Hit that over. There we go, operational headaches. Here, I got it. We'll just flip them all down, it's fine. There we go. Am I on the right one? Yeah. So the main was around operational headaches. Because we're using ephemeral storage and not utilizing the EBS service, we had to maintain things like encryption at rest. So because of that, we had to provision our own encryption keys, make sure those were rolled, make sure our data was in compliance, and just provided a lot of operational overhead for the team. Our data retention was not being met. We actually claimed that we retained 90 days, but we were actually retaining 30 days. And that was just because the cost was way too high. What we noticed was, so the cost was way too high. We had to allocate storage based on how many instances were actually inside the cluster. So what this is meant to show is every time we needed to add a new instance in to scale up our storage, we actually had to add a new instance into the cluster. And whenever we did that, there was always kind of this gap between, here, I'll push it. There was kind of this gap between what was allocated and what we were actually using. So we found there was a pretty big gap between money lost on what we allocated as we scaled up. And it was just generally bad practice to have the storage allocated tied to how many instances were inside the cluster. So we kicked off an investigation phase and started looking into how we could redesign this both around better performance and around better costs. So that led us to a few different things to investigate. The main was around user patterns, how people were actually accessing the data inside the cluster. So as we started analyzing those queries and talking to people in support and in engineering, we found that generally they only really cared about the last few days worth of log data. It was either used to debug a production issue or gather data for a customer within the past few days. And if the data was older than that, they were okay waiting a few extra seconds for a query. So that was really valuable. That allowed us to kind of define our performance requirements around ingestion, search time, and make sure we're providing customers with a good experience. And the other investigation point was the fact that they announced a bunch of new volumes right when we started this project. So the timing actually worked out pretty great. So this was me. Man, all my transitions are broken. So this was me when the email came out. We began to look into this as a solution to allow us to meet our retention periods as well as a way to decouple our instances from the actual storage amounts that were met. We began to theorize that the performance of the new cold and warm storage options would give us good enough performance for some older data while still utilizing SSD for ingestion and search of the most recent data. So that gave us a really clear line of sight into a new proposal on how to redesign our cluster. The proposal made up a few different pieces. The first was to just go all in on EBS. It reduced the complexity around encryption, and it also decoupled the instance count from the storage that was allocated. The second proposal was to break up the allocations into three distinct storage tiers. The main being the hot storage around the SSD ingestion and the most recent data, and then promote that data off into other tiers as it aged off. And the other proposal was to redesign our instance types inside each layer to better optimize around performance and cost for each layer specifically. When we were using the I2 instances, we were getting the same performance for data from 30 days ago as data from the last second. And we just found there was a big gap between the performance we allocated versus how people were actually using it. And that was the big differentiator around cost. So this is kind of how the proposal broke down. When we put rough numbers together, we said the past 7 days sounds good. We'll keep that on hot GP2 storage. When the 8th day rolls around, we'll promote that off into the ST, and then we'll keep data older than that on the SC storage. That should say 90 days. Just pretend it says 90 days. So Elasticsearch has a great way to manage this. They have a tool called Curator, which allows you to define buckets of where you want the shard data to live. And so we use this as a way to automate the provisioning of that. So I'm going to do a quick walkthrough of what that looks like. So here you can see it's January 1st, 2016. We have data coming in on the primary hot storage, and you can see there's currently no data on the other two storage layers. So as we move on to January 8th, that data is now older than 7 days. We'll kick off a promotion process to move it into the warm layer, and the cluster will just rebalance it naturally. So on the 8th day, you can see data from the 1st is now moved onto the warm, and the data from today is now being ingested on the primary layer. So as we move on to the 15th, the data from the 8th is now older than 7 days. We'll kick off the same process, promote that data over. So now we have both those inside of there, data from the 1st to the 8th, and now the new data is coming in on the primary layer as expected. And so then on the 30th, the data from those two, from the 1st has now aged off. We'll run the same process and promote that off into the cold storage. So that ends up with something like this. So the data will naturally tier off as the data ages. So here's a little bit how that looks inside of Elasticsearch. Elasticsearch has the idea of routing allocation, which is where you place the sharded data inside of your cluster. So any new data coming in would be allocated with a hot tag, which is what we would build the primary SSD volume data nodes with. So that would ensure all data coming in comes in on the SSD volumes. And then we would just run a cron job to update that when the data becomes older than 7 days, and then the cluster will naturally rebalance that. And you can't do a talk at Amazon without a topology graph, so this is a little bit how our cluster looked. You can see we're distributed in multiple AZs, and this is meant to show the 3 different volume types on our data layers. So the bosses were super happy. We cut cost. We were able to utilize different instance types. We also found as part of this we were over-allocating our JVM heap memory, so we were not using compressed pointers inside the JVM. Memory is one of the most expensive Amazon resources, so being able to compress that and utilize it on better instance types made a big deal. We took this time to optimize a few other things. The legacy cluster wasn't built with any kind of template or CloudFormation, which was kind of a mess for management. So we utilized a great open source tool named SparkleFormation. SparkleFormation is a Ruby DSL language meant for writing reusable code to generate CloudFormation templates and then promote those out. So we were able to build 3 distinct data layers inside different templates and update those dynamically as we scaled up. We also had a lot of issues around data transmission from the client to the server. Because we log a lot, that data would buffer locally on each client, and if we had any network instability into Amazon, some of that data could be lost or delayed. So we utilized 2 new open source tools. FluentD is what we deployed on every client node. And then we deployed Kafka, which is a great reliable message buffer for the buffer between clients and the servers. So this is a little bit how that looks today. It doesn't have my camera. So inside the data center, you can see we deploy Fluent on each client node. That watches a subset of logs, feeds those into a Kafka topic on 1 or more partitions. And then inside Amazon, we point those at each specific pod or VPC, read that data out, and then feed it into our primary data node cluster. And what you would see here is the other 2 data nodes below Elasticsearch as the data promotes out. And I'll let David talk a little bit how it went.
Okay, so where we got to here, we're pretty proud of. So overall, we operated out of 2 regions, the US and Europe. Overall, our complete expense in the project was basically cut in half, so that was great. We are able to increase our data retention to 90 days and in an expandable way. So what that ended up was a real win in terms of delivering what we needed to. In addition, the whole way to scale the system got much more predictable because we're adding servers and storage separately. We can, grow storage in a more incremental way and keep it closer to the actual needs that we have, and without unnecessarily provisioning additional EC2s for compute. And then when we needed to provision additional EC2s, or if we lost an EC2 for maintenance reason or what have you, the whole cluster didn't rebalance. We were able to just replace that without a lot of maintenance window. So that was really great. Overall, we were able to utilize a number of Amazon features. For example, now we can take advantage of built-in EBS encryption, and so we didn't have to bring our own code in, and that was much easier to deal with. And generally, the cluster stability increased, pretty massively. Everyone likes to see, dollars result, especially in a use case like this. So what we had here is a figure where we spent internally around $600,000, and you see we reduced that to about 300, which is a pretty good number for a reduction. What's most interesting is that we have a 5x increase, or rather a 5x decrease in the cost per storage unit. So that's a pretty significant benefit that we delivered inside the business. I guess our takeaways from the project are really, as Kyle mentioned, when you embark upon a project like a project, really look at the use case of how people use the data. Don't just assume that, okay, we have so much storage need, and so we'll just provision a whole bunch of storage, basically optimizing for the most demanding storage requirements. So a little bit of thought in terms of that will go a long way in both the costing and the flexibility. Look and find where the performance really matters. Sometimes people just sort of believe that, oh, this is going to be I/O bound, so I'm just going to choose this type of EC2. That could be a very pricey decision. So really spend some time thinking about where performance really matters and where it doesn't matter, and where you can optimize cost or buy yourself a little bit of flexibility. Especially be careful about buying more than you need in terms of over provisioning. And so we have more smaller machines and more granular capability, and always try to use AWS services wherever you can, because that's less for you to have to build and maintain. So, so thanks for our session. Thanks, Kyle. And I guess we'll hand the microphone over to the Videology guys. Thank you.
All right, so we are Videology. I am David Ortiz, a senior software engineer.
Paul Fredrickson, principal DevOps engineer.
And we are in support of the big data team at Videology. So in this session, you can expect to get an intro of who we are as a company, the challenges we were facing on Hadoop, as well as how we moved to an EBS-backed cluster and why we are much happier engineers as a result of this.
Just a quick overview of Videology, if nobody's ever heard of us. We were founded in 2007 by Scott Ferber, who also co-founded advertising.com and ended up selling it to AOL for $500,000. Our corporate headquarters is in New York, but our technology team is actually based in Baltimore, Maryland. As you can see, we have offices all over the world, Sydney, Toronto, London, Singapore, Texas, California, Baltimore, obviously. Our employees, we're actually, I think, over 400 people now. We're growing very quickly. As you can see, here's some of our recent client wins: Sky Media, AT&T, Adobe, Rogers, a lot of media companies. More marketing slides for you guys. The industry accolades: best digital video ad platform, most sophisticated media optimizer, and 6x higher brand lift from a Nielsen study.
All right, so since we are about to go in-depth into how our Hadoop cluster runs, I figured I would give a quick overview of Hadoop just in case people aren't familiar with it. So Hadoop is a platform that is based on how Google used to run their infrastructure, and it provides scalable cluster computing on commodity hardware as opposed to having to go buy high-end specialized stuff. So this doesn't mean cheap, but readily available servers that you could order off the shelf from like Dell or any other provider as opposed to the high-end stuff. The big thing with Hadoop that's different than some of the platforms that came before it is it tries to move the compute to the data instead of bringing the data to your beefy compute nodes. It's broken down into two parts. You have HDFS, which is your file system, so to speak, and that is done by allocating block storage on a bunch of different nodes and just kind of round robin writing to them into large file blocks of about 64 megabytes so that you can take advantage of sequential reads. And then, as you can see in the slide, the data node would be the storage provider there, and then you have the name node to track everything. You also have what's called Yarn, and that is your compute framework. So that basically just tracks the resources available on the node managers and allocates them the jobs as they come in from whatever user or code is submitting it. So where does this fit into Videology? So we have a high-level architecture diagram. Since we are an ad-serving media company, we have a bunch of ad servers that are running on AWS, which generate a ton of logs, which go to S3. So from there, we use our Hadoop cluster as kind of a giant ETL pipeline. So we have warehouse jobs that pull everything off S3, clean the data up, normalize it if needed, stick it into the file system, and then we have other extract jobs that run aggregates over it, push it back out to S3, where it's then loaded into some various reporting systems. We've got data warehouse, our analytics warehouse, and then some operational databases that people inside the company use to track performance. So just to provide some metrics, this is running roughly about 1,200 jobs per day. It's a mixed workload of copies, Hive scripts, which is a SQL over Hadoop framework, and then Crunch, which is a high-level Java framework for writing MapReduce jobs. We process about 7 terabytes of data on the input side per day, and I already mentioned the systems we feed.
So you can see our original production environment. These kind of follow the components that David just talked about. Most importantly, the 30 worker nodes that we're running on the CC2 8XL instances. 32 CPUs, 60 gigabytes of RAM, and 3.2 terabytes of storage per instance. And this original production environment resulted in this. So lots of hip chat messages of why is this instance down? You can't really see it very well, but it's essentially, hey, the status checks are failing on these machines, and me responding with, well, that's usually not good, let's build new ones.
Yeah. So some of the other problems beyond reliability, we had some issues with scalability where we were very pegged on the system. As you can see, our memory was always full, so once we would have any kind of increase in data volume, we would find ourselves having to frantically contact Paul and his friends to spin up more nodes for us. We also would have issues just in terms of the latency of the jobs. Like some of the copy jobs from S3 would end up taking like 30 to 40 minutes to run for an hour's worth of data, which as you can imagine is somewhat untenable when you're trying to do that and then also process the data as well in the span of that hour. And that brought us to deciding we needed to do something different. So after the CC2 line, Amazon kind of moved to a lot of their instances being SSD backed, which is great as a general thing, but when you're trying to run Hadoop and you need like 100 terabytes of storage on your cluster, that's a lot of nodes to have to spin up if you're using ephemeral storage. So we kind of talked to our Hadoop vendor, which was Cloudera, and kind of said, hey, do you guys have any plans to support EBS? Because we really need to move to nodes that use it.
No.
And we kind of, yeah.
No again.
So they kind of seemed open to trying to do like a proof of concept with us. We could never quite get everything going with it, but they were like, you should try these D2 nodes. They're really cool. So we started testing those in March of this year. That didn't quite work, as you could probably guess by the fact we're presenting at the EBS session right now. So as we're starting to go back to the drawing board, not Cloudera, AWS announced the SC1 and the ST1 volumes of storage. Since we are running highly sequential workloads, that kind of sounded perfect for what we were trying to do. So,
and it was exactly just like Zendesk, where it was we're in the middle of it, and boom, there's the whole thing. And I sent it to his team and said, hey, look at these things. These I think will work. So.
Yeah, and we kind of looked and went, yeah, those will work. Let's do that. So we started designing the cluster around that in May, and then through June and July, we were kind of testing the different configurations of storage. We started out with an SC1 configuration because it was the cheapest, and cost savings, yay. So we decided to try that. That didn't quite give us the performance we needed, but it was promising, so we moved up to the ST1s with smaller volumes, and then decided just to go for broke and get the volumes that would give us the fastest throughput just to be safe. And in August of this past year, we went into production with this, and after about 2 years of service, the CC2 cluster finally died.
So this is just another way to look at our progression that we went through. So we started with the CC2 8XLs. They were old, not enough disk. They failed pretty regularly, and they just cost a lot of money for what we were getting. The D2 8XLs, as was mentioned, we moved to tons of disk, more disk than we could ever use, but just didn't give us the resources we wanted. And they were also very expensive, made it very difficult to scale at any kind of large amount, essentially. Then we looked at the M4 10XLs, CPU, memory, disk, everything was perfect, complete nirvana, happiness ensued.
So to prepare you for the next slide, that D2 8XL should actually say not enough CPU rather than not enough memory, because you will see they actually have lots of memory on in a second.
So here's the D2 8XL. So you can see the worker node's the most important part here that we're focused on. We started with 10 of them, and it had 36 CPUs, 244 gigs of RAM, and 48 terabytes of storage, which was way more than we needed.
Yeah, for reference, in the old cluster, we stored about 80 to 100 terabytes of data at any given time. In this cluster, we had 480 terabytes. What we didn't have was enough CPU cores to actually run an hour of data. So our initial tests looked awesome with this. Like, the disks were blazing fast, I/O was nice. And then we started trying to run our full workload, and it just ground to a halt because it couldn't run enough parallel tasks.
I think we're actually really close to going in production with this, because we went to it and we're like, let's start actually running production data on it, and that's when it fell apart for us.
Yeah, it was the stress testing portion of things. And just with the cost of the workers, it was too much to add that many more to fix it.
So then we moved on to the M4 10XLs with the SC1 prototype. Our vendor, Curator, mentioned to us, they said the SC1s look like the bandwidth is enough, this should be able to handle it, so we jumped into it. We were able to scale out, and all of this was, we tried to stick, to give some context with how we chose the number of nodes and storage, it was all cost driven. So we wanted to keep kind of the same amount of costs in budget so that we could, it was easier to sell, and it was, we wanted to be able to show that, we're making improvements with the same amount of money. So 18 worker nodes, 40 CPUs, 160 gigs of RAM, and 4 terabytes of memory. The big problem here was just the SC1 just wasn't fast enough for us. So when we were going through and looking at the numbers and looking at CloudWatch, we just found that we were hitting the bandwidth restrictions on the SC1. Then we moved to the ST1. Pretty much the same numbers there. The only difference is we started with 4 terabytes of ST1 storage that we ran into again where we weren't quite getting enough bandwidth that we needed. So moving to 8 terabytes actually doubled that bandwidth for us and allowed us to run our production workload on it.
Yeah, and this is actually the configuration that we went with in our production system. And right now we're running a few extra nodes out of an abundance of caution as we hit Q4, since we are in advertising, which Q4 is by far the busiest time of the year. And we are also adding a lot of extra workloads that didn't used to be on the cluster at this time. So we figured we'd play it safe during the most important time of the year for the business. But this is basically our architecture now. So here is a diagram of our PagerDuty pages generated by the CDH cluster from January up until the beginning of October. So as you can see, we've got some spikes. Those were our critical incidents on the old cluster. Let's see, the one in January was when our master node that ran all the services for Hadoop went down. The other ones were pretty much related to bad data nodes, just kind of slowing everything up and causing delays. The other 2 big spikes. And you can see we went into production on August and kind of have a downward trend after that. Some of the benefits of this have been more sleep. I can go home and spend time with my kids and my wife instead of spending time with my laptop watching to make sure that we're not falling behind. And then Paul's had some benefits as well.
Yep, and just to show this graph too, this really makes in our organization, we really pay attention to PagerDuty and Pages. We have kind of a misery index that we show for our engineering, and so showing this is really great and makes the team look good, and everybody sleeps, which is good.
So we also have some benefits with relation to capacity. If you remember from the problem slide, that graph of a solid field of blue was our memory utilization on the old cluster. If you're looking at this one, that top graph is now the memory utilization of our cluster. Or sorry, the bottom graph is the memory utilization. The top one is the cores, which is now the more limiting factor of the two, and you can see we still have a pretty decent amount of extra capacity there. And this is important because we don't just want to kind of keep everything the same. We are looking to improve our platform, improve our SLAs, our reliability. Some of the other tools that we're looking at, we've had some issues with starting to overload Redshift with running too much stuff on it concurrently, so we're trying to offload some of that onto our cluster, and we have the bandwidth to do it now. We're trying to move to a more stream ingest model. Flafka, which we have there, is similar to what they were talking about with Kafka, with Flume in front of it, which is a tool for ingesting into Hadoop. And we're starting to look at some other database technologies like HBase and processing frameworks like Spark that tend to be more memory intensive than your normal MapReduce, which tends to require 2 gigabytes of memory per core of CPU. We're also more resilient to our log volume increases now, because both from a capacity perspective, and we can expand our storage without having to spin up a bunch of other boxes. So like, for example, if we decide, holding 20 hours, or not 20 hours, 2 days of request data is not quite enough, we can just add some more drives to the boxes and store like 7 days without needing a bunch of new processing power that we would never use, because while we would have the data there, we're not normally looking that far back at any given time.
The other thing is with all this added capacity, they were actually a 25% data increase in one day, went completely unnoticed. Some people were looking at some graphs and they're like, this can't be right. And we got it and nothing paged. In the old cluster, that would have been a downtime event. Like, it would have been a pageable event for us.
That would have been another nice little spike on the pager graph on the previous slide. All right, so to come up with some of the kind of financial benefits, as you can see, while we initially started out controlling for cost, once we moved to the more expensive storage, it was a little more expensive, but we really liked the performance we were getting out of it, so we were able to roll with it. But to try and kind of normalize that against the old cluster, just did some math with it. So the old cluster was always 100% utilized, which means that our cost for processing that hour of data was the $21,500 the cluster cost per month. Since the new cluster is 60% utilized, if you normalize against that, we're using $15,300 worth of capacity to process slightly more data than what we were processing at that point. So the other fun one there is since all of our stuff is measured by requests, whether it's ad requests, bid requests, the events from our video player saying like we've seen this many clicks, we've seen this many views, that kind of stuff. If you look at the cost to process 1,000 requests on both clusters, on the old cluster it would have cost us like 9.3 cents. On the new cluster, instead, it is costing us about 7.3 cents. So that's, give or take, like a 20-25% decrease in the cost for that processing.
And this was all due to these ST1 and SC1 EBS volumes coming out, because without them we would have been probably spending a lot more money on D2 instances.
Or GP2,
or GP2s,
SSD-backed storage. The other thing that's been nice with this cluster is since it is somewhat tolerant to our ebbs and flows of data, it is a little easier to budget for if you are the type who is doing that sort of thing, because you're not spinning up X number of nodes every couple months when you have a data issue where X can be anywhere from like 3 to 5, which definitely spikes your budget a little bit more on that end.
Yeah, and it's also easier for us to scale out too. The costs of the M4 10XLs and the amount of space and everything, we can scale out. Once we need more resources to do that. So it's makes everybody happier and, like you said, easier to budget for.
These numbers, the ones on the left are per month. The one on the right is the cost to process 1,000 requests regardless of time. All right, so that concludes our presentation. If you have any questions for us or Zendesk, we're going to be down at the front after this. And remember to complete your evaluations.